Good morning students, welcome to Lakshya Academy YouTube channel. Yesterday we discussed some numericals and today we discuss some more numericals on energy band gap. First problem, a semiconductor diode laser has a peak emission wavelength of 1.55 micrometer. Find its band gap in electron volt. Electron volt is another unit of energy. The SI unit of energy is joule. 1 electron volt equal to 1.6 into 10 power minus 19 joules. Energy is given by E equal to h nu, which is hc by lambda, nu equal to c by lambda. C is speed of light, which is 3 into 10 power 8 meters per second. Wavelength is given in micrometer, micro means 10 power minus 6. So E equal to hc by lambda 6.63 into 10 power minus 34 into 3 into 10 power 8 by 1.55 into 10 power minus 6. We get the answer in joules. To convert into electron volt, we have to divide with 1.6 into 10 power minus 19. By simplifying, you get the answer of 0.8 electron volt. So in this case, the energy band gap is about 0.8 electron volt. Next question, calculate the wavelength of emitted radiation from gallium arsenic which has a band gap of 1.44 electron volt. Energy gap of semiconductor E equal to h nu, h is Planck's constant, 6.63 into 10 power minus 34 joule second. Joule second is SI unit of Planck's constant. So we can write lambda equal to hc by E. Substitute the values, 6.63 into 10 power minus 34 into 3 into 10 power 8 divided by 1.44 into 1.6 into 10 power minus 19 electron volt converted into joules, and simplifying we get 8.63 into 10 power minus 7 meter. The SI unit of wavelength is meter. Angstrom is another unit of wavelength. Next problem, if a light emitting diode emits light of wavelength 580 nanometer, then energy gap between valence band and conduction band is. Wavelength is given in nanometer. Nano means 10 power minus 9. Answer is given in electron volt. Lambda equal to 580 nanometer, 580 into 10 power minus 9 meter. Nu equal to c by lambda, h nu equal to hc by lambda, energy equal to hc by lambda. So 6.63 or 64 into 10 power minus 34 into 3 into 10 power 8 divided by 580 into 10 power minus 9. and we get 0.034 into 10 power minus 13 joules. To convert joules into electron volt, we have to divide that value with 1.6 into 10 power minus 19, 0.034 into 10 power minus 13 by 1.6 into 10 power minus 19 electron volt. We get 2.1 electron volt as the answer. Fourth one, the energy gap of silicon is 1.14 electron volt. What is the maximum wavelength at which silicon will begin absorbing energy? Energy E equal to Hc by lambda, lambda equal to Hc by E, and convert electron volt into joules. 1 electron volt equal to 1.6 into 10 power minus 19 joules. We get 10.901 into 10 power minus 9 meter. 1 angstrom equal to 10 power minus 10 meter. So 10.901 into 10 cube angstroms. So 10,901 angstroms. The maximum wavelength obtained as 10,901 angstroms. The energy gap of silicon is 1.5 electron volt. At what wavelength the silicon will stop to absorb the photon? This is very nice problem. Fifth one, lambda equal to Hc by E, and energy is given in electron volt. We have to convert into joules. 6.6 into 10 power minus 34 into 3 into 10 power 8. Planck's constant 6.6 something into 10 power minus 34. So here I consider 6.6 only, divided by 1.5 into 1.6 into 10 power minus 19, 8.25 into 10 power minus 7 meter. Convert to angstroms. 8.25 into 10 cube angstroms, because 1 angstrom equal to 10 power minus 10 meter. So 8,250 angstrom. So the photon having the wavelength equal to 8,250 angstroms or more than that will not able to overcome the energy gap of silicon. To stop to absorb the photon, the wavelength range is 8,250 angstroms. Sixth one, the electrical conductivity of a semiconductor increases when electromagnetic radiation of wavelength shorter than 2480 nanometer is incident on it. The band gap for the semiconductor in electron volt is. Generally, energy E equal to Hc by lambda. To calculate the problems, consider that Hc equal to 12,400 electron volt angstroms. For the calculation purpose, in simple method, Hc value 12,000, nearly Hc value 12,400 electron volt angstroms. Here I consider 12,375 electron volt angstroms. Hc value. Note down that Hc value 12,375 electron volt angstroms. So in that case you can simplify in easy manner. So 12,375 by lambda. Lambda also we have to write in angstroms. So 24,800 angstroms. So simplify that. Band gap 0.5 electron volt, nearly. Seventh one, what is the resistance of an intrinsic semiconductor at 0 Kelvin? This is a problem in H.C.VERMA book, page number 417. What is the resistance of an intrinsic semiconductor at 0 Kelvin? Yeah, already we discussed that at 0 Kelvin, semiconductor behaves as an insulator. A semiconductor has a medium resistance and insulator has a very high resistance. At 0 Kelvin, valence band is full and the conduction band is empty. No electron is available in the conduction band. The intrinsic semiconductor at 0 Kelvin acts as an insulator and offers very high resistance, infinite resistance. This is also another problem of H.C.VERMA book. Eighth one, in a photodiode the conduction increases when the material is exposed to light. It is found that the conductivity changes only if the wavelength is less than 620 nanometer. What is the band gap? Band gap E equal to Hc by lambda. Hc value 12,400 electron volt angstrom. Here I consider 12,420 because H value 6.6 something. So based on that, that value changes. So the band gap is about 2 electron volt. Ninth problem, find the maximum wavelength of electromagnetic radiation which can create a hole electron pair in germanium semiconductor. The band gap in germanium is 0.65 electron volt. Band gap is given, energy is given in electron volt and Hc by lambda. Hc value 1242 electron volt nanometer by 0.65 electron volt, and convert electron volt into joules, or electron volt get cancelled. So we get 1.9 into 10 power minus 6 meter. Meter is the SI unit of wavelength. 10th one, suppose the energy liberated in the recombination of a hole electron pair is converted into electromagnetic radiation. Maximum wavelength emitted is 820 nanometer. What is the band gap? Lambda is given 820 nanometer or 820 into 10 power minus 9 meter. Minimum energy released in the recombination of a conduction band electron with a valence band hole is equal to the band gap. That minimum energy is nothing but band gap of the material. Band gap E equal to Hc by lambda, and by substituting the values you get 1.5 electron volt. Do it. Students, note down that Hc value, take 12,400 electron volt angstroms in most of the cases, that is better.